Okay, I didn't realize that I'd put that as the title on the thing. So thank you very much for inviting me to speak, and thank you very much for the second title of the talk. So this is the stuff I'm going to be using, but I thought I'd start, since it's a symmetric groups conference, with something about symmetric groups. So, I wanted to use slides because this is like the biggest screen in the history of the world, so I thought it'd be a waste. So let Sn be the symmetric group on n letters. And we're going to be looking at its representation theory over a field of positive characteristic. Now, we probably all here know that the representation theory of Sn is indexed by partitions. And thanks to work of Kovanov-Lauder, Brundin-Kleshchev, and Rouquier, we know that we can ask what does the decomposition matrix look like, but in a more richer structure would be what does the graded decomposition matrix look like. So representations are graded. So this emits a grading, and then you can say, okay, well, what do the simple constituents look like? But you can also keep track of the graded shifts of these things. So if you forget this grading, then you just get the regular decomposition numbers. Okay. So now, this is an old story, and it began, I guess, with Lustig, but not really. But, you know, P greater than H. We've done this for a while. We thought, it's too much to understand everything, so let's let P be greater than H. And then Anderson, Janssen, and Zergel said, oh, well, what if P is much bigger than H? So what is H? So we're going to restrict the partitions so that we consider the ones with at most H columns. So we're not going to consider all spect modules to begin with. We're going to restrict and just think of those labeled by partitions with at most H columns. And what we're going to do is consider the subcategory of representations for the symmetric group whose simple constituents are labeled by these partitions. Okay. And this is a subcategory which is rich in structure, but it's also understandable for P greater than H in terms of the P canonical basis. This is Risch and Williamson. It's now actually understandable for P less than H as well, but I'm going to segue. So for me, what I'm actually interested in, because I can prove results about it, is that what if P is, well, we do some results for P greater than H. So if P is much bigger than H, the representation theory of this subcategory is much simpler. It simplifies, and rather than having to understand P canonical bases, you can go back to almost the easy case now of Castan-Lustig theory. And I should remark here that even though Anderson, Janssen, and Zergel talked about P much bigger than H, it's the decomposition numbers for symmetric groups, that wasn't actually covered in their result. You have to look at Risch-Williamson for that, because it's about tilting characters for quantum groups. So in order to understand decomposition numbers for symmetric groups. Okay. And if you didn't like any of the words I used, like subcategory and blah, 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 since we've been talking about Schur-Weyl duality anyway, you might as well just say, I'm interested in the chunk of Sn which I see in classical Schur-Weyl duality with the general linear group of H by H matrices. Okay, so far so good. This is the symmetric group. Goodo. Oh, sorry. All right. yeah, go ahead.
Is H fixed?
Yeah, so, is it the Coxeter number? It is the Coxeter number, yes. So that's why it's GLH. I don't think I screwed that up. But you pick an H, and then for whatever H you pick, so you can vary it if you like, you just let P be bigger than that H. And this is exactly what, if you want to talk in terms of Lustig, then take the general linear group and just let P be bigger than the Coxeter number. But we're working on the other side of the duality, is essentially the idea. Okie dokie. So how do we study these things? So we're going to take our set of partitions with at most H columns, and we're going to consider them as points in Euclidean space. we'll equip this space with the action of, with an alcove geometry of type AH-1 inside of affine AH-1, and we'll see some pictures in a moment to see what that means. So, for example, if H is 2, oh, I've got pens here. So, if H is 2, then we're very familiar with the idea that representations of SL2 are indexed by natural numbers. And if H is 3, we see triangles going like this. And if anyone doesn't like the parabolic part of this geometry, just notice that if I'd carried on in this way, that would be affine, that would be S2, but I've actually, S2 geometry, but I've taken a dominant region, so I've factored out by the reflection of the first S2. And here, I could carry on in all directions, and that would give me S3. But I've quotiented out by, so I've considered 1/6 of this region, 6 regions, and I've considered only 1/6, which is the size of S3, and that's where the parabolic part comes in. Okay, so tale as old as time, we think about decomposition numbers for symmetric groups, or if you prefer, general linear groups, in terms of embed points into here and look at reflections that relate them. So the purpose of this talk is twofold. One, so this is the symmetric groups part of my talk. What if we don't just consider the points themselves, lambda and mu, but we consider the path obtained from walking to the points in the first place? Do we get more information? And this will make more sense when we go on to the next slide. And then the other part of the talk, so I guess these are the two titles of my talk summarized in two nice boxes. What can we do for other complex reflection groups? So is this something that only works for SN, or does it also work for other complex reflection groups? So Ariki-Koike algebras, things of the form like that. Okay, so those are the two parts of my talk, and hence the two titles. So part one, paths, not points. So the strong linkage principle in its classical form says we say that two things are strongly linked if you can get from one to the other by just doing successive reflections towards the origin. Okay, and what the strong linkage principle says is if they're strongly linked, so a strong linkage is a necessary condition for decomposition numbers to not be 0. Okay, so let's draw a picture. So I am going to be interested in multiplicities. So I'm working L mu. So remember, I am working in the symmetric group, if you like. So I could actually use spect here. I'm not working in the general linear group, so everything is Ringel-Joule. So if you're thinking everything's backwards, it's because we're in the symmetric group side, not the general linear group side. So I want to know where does this simple module appear? Which spect modules can it appear in? Now I have to, this only works if I reflect to get mu closer to the origin. So alpha is obtained by reflecting through this wall here. And clearly alpha is closer to the origin than mu. So if x is equal to alpha, not equal to 0 implies x is in the set alpha. Or it could also be in beta or gamma. So I've reflected through this wall to get alpha, and I can reflect alpha through that wall to get beta. Good. So beta's clearly in the set. Now I can also reflect alpha through this wall here, and I'd get gamma. And then I can reflect again and reflect them both towards delta. So there we go, delta. And finally, the alcove containing the actual origin, lambda. So what the strong linkage principle says is that if this decomposition is not 0, then x is in this set. That's what it says. You have to be able to get to whatever x is by successive reflections taking you closer to the origin. So there's the classical strong linkage principle. Now, instead of just doing that, I said I promised you I would look at paths. So let's let mu be the point 2, 1 to the 12, which we draw like so. 2, oh, okay, I've drawn too big. 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Still too big. 12. Okay, so there's 2, 1 to the 12. I'm going to draw a path from the origin to that point. Now I'm going to consider what paths I can obtain by reflecting this guy. So let's see what that means. So here is my path. It starts at the origin and it goes to 2, 1 to the 12. How does it do that? Well, I'm embedding via the transpose map. So rather than so if my directions are epsilon 1, epsilon 2, epsilon 3, well, I take this guy to 13 epsilon 1, because I'm embedding via the transpose map, plus epsilon 2. Because remember, I have at most h columns, with h is 3 here. I go 13 and then 1. And how do I do it? Well, the path I actually use is I go plus epsilon 1. So that's going in that direction. Ding. And then I do plus epsilon 2. And then that takes me there. And then I've just got a bunch of epsilon 1s. So that's the path I start with, t mu. So I fix this path. Now I want to consider all paths I can obtain by reflecting it towards the origin. So let's do that. So this is one path. Now here I've represented both the original path, which goes to here, and its reflection through this wall. Great. So I've got two paths now, but I want all of them. So what if I reflect here instead? So if I reflect here, I get a path that terminates there. Now, if I now consider, so what if I take the path and then I reflect ding there and go along and ding and up? Great, there's another path. You can probably see what I'm doing now, another path. And then there are two more paths. Oh, okay, now there are two more paths, and they just go over points I've already seen. So that's ding, 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 ding. Great, so those are all the paths I can obtain by reflecting my original path, t mu, up into the origin. Now notice the places that these terminate are exactly the same places as the strong, we colored in before with the strong linkage principle. So note, path from this set of paths I've obtained by folding up this guy to a given point lambda is non-zero, or non-empty. So sorry, this should, I guess, be x rather than lambda in order to be consistent with this. But this set is non-empty if and only if they're strongly linked, right? So there's a path ending there, 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 and there. And those are the points that I started with over here. Great, so far so good. So this is the set of paths, and notice that this set is non-empty if and only if they're strongly linked. But what if I now throw away all the paths which leave the dominant region? So any path which touches a wall is thrown away. So if a path touches a wall, we say that it's left the dominant region. So I shall now click and mildly change the coloring. So now I've only got 4 paths in total. The one that ends here, this guy, and then these two here, because the other guys all touch the wall. Right. So I've now considered the subset of dominant paths, if you like, hence the plus sign. And these ones never leave the dominant region. So now, a sneak peek of the result. If we, this is the ungraded version. So our result is that if I consider the decomposition number, S lambda delta mu, then this is bounded above by the number of paths in this set, right? So, and here, notice there's a plus sign. So this is better than the strong linkage principle, so you might call it the super strong linkage principle, with a hyphenate so people don't think you're talking about supergroups. Now, if we go back to the other side, notice that, so the strong linkage principle would say I could have a decomposition number labeled by this guy, this guy, this guy, this guy, this guy, this guy. So we've already, by using dominant paths, we know a better result because we've already ruled out that this decomposition number has to be 0, which we couldn't see using the strong linkage principle, but we can see that it's 0 using the super strong linkage principle. And the same for this guy here. But not only do we bound above by 0, which is the classical sort of result, we also get other bounds for these decomposition numbers. So the only ones that can be non-zero are this guy, this guy, this guy, this guy. And moreover, the maximum they can be is 1. So it's super duper, I guess. It's super in two ways. It's more 0 bounds, and the bounds that we do get are more interesting than just 0, not 0. Okay. Now, I said this was the ungraded version, so why don't we grade it? So here, the points in that I just labeled are actually these guys. So remember, 2, 1 to the 12 was our point here. And in fact, these ones are these 3 here. So here are the paths which terminate these points. I would like to associate to them all a degree so that I can give you a graded decomposition number upper bound. How do I do this? So the first path, it just walks all the way out the origin, fine, 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 fine. So he's a 0, nothing happens. Now the second path, he just walks tra-la-la-la-la-la-la-la, and then he bounces back towards the origin, and on bouncing back, his degree goes up by 1. So that's a 1. Now here, I go tra-la-la-la-la-la-la. Now I bounce. So now at this point, I've now got degree 1. Bounce, I've now got degree 2. So he has degree 2. But now notice here, this guy, if I go like this, whoop, so now he has degree 2 at this point, but now he bounces away from the origin, so he has degree 1. So bouncing towards the origin increases the degree, bouncing away from the origin decreases the degree. And so each path has a degree which goes up, down with each reflection towards, away from the origin. Great. And so, in fact, the graded decomposition numbers here are bounded above by the degree k paths. Right? So that's all good. So there's a new upper bounds for graded decomposition numbers of symmetric groups in terms of the dominant paths in our geometry. And what's nice is not only is this a nice result for the symmetric groups, but it's also going to generalize to all these cyclotomic Hecke algebras. But I just thought I'd state it in a place where we sort of felt familiar to start with. Great. Okay, so here, this gives us the following bounds on decomposition numbers. Obviously, the spect module labeled by a given partition will have him as a head, simple head in degree 1. And then here we get bounds of degree t to the 1, t to the 1 for him, and finally t to the 2 for him. Oh, sorry, it's 6 in this case, because that's what I chose for my thing, so I guess this would only work for E. It would have to be a quantum thing, but I can draw the same picture with any prime, and it all works the same. And these bounds are sharp in this particular example. So here, this actually calculates these decomposition numbers. Okay, so that's the super strong linkage principle part of the talk over and done with, I guess. So let's see what happens next. So what about if we wanted to look at deformations, these guys, so the Ariki-Koike algebras. Okay, so I'm going to fix a couple of integers. One would be a quantum characteristic, if you like. The other is the rank of my symmetric group, Sn. And then I'm going to fix a charge, a multi-charge, to be a L-tuple of integers. And K is an arbitrary ring. Ooh. So hopefully most people are now familiar with this idea that there is a new presentation for the Hecke algebra. Oh, the word quiver there means that it's just the first presentation of this, I guess, where we have idempotents labeled by n-tuples of integers, which come from z over ez. There you go for I there. Along with things that look like braid relations and things which behave like juicy Murphy elements. Okay, and that should actually have r equal to n as well for that last one. So it's generated by these guys, subject to some new relations, which are deformations of the old ones, a bit weird. So the old braid and reflection relations, they get deformed in a weird way, and you also get some extra relations because you include these in your presentation, which you wouldn't bother with normally in the symmetric group world. But we also have this cyclotomic relation, which says, okay, I'll get rid of this now. Now, the point of this cyclotomic relation is, notice that it only depends on the reduction modulo E of my L-tuple of integers. So the cyclotomic relation says that EI Y1, does it have a Y1 there? Yep, good. So the number of sigma k such that sigma k is congruent to I1 mod E. And 1 less than or equal to k less than or equal to L. So maybe you don't know what this presentation is. The only thing you should care about is that this presentation, this quiver-Hecker algebra, is defined only in terms of the reduction modulo E of this parameter. So Ariki-Cauchy algebras, you can define them for any L-tuple of integers, but up to isomorphism, they only depend on the reduction modulo E of that L-tuple. And then the moral is, perhaps, even if up to isomorphism, they don't depend on this sigma, maybe it is secretly hidden there telling us more information. This only depends on the reduction modulo E of sigma. So, oh, that wasn't supposed to be a kappa. Oh, I hope that that didn't happen throughout the talk. I'm going to hopefully denote it Hn, well, here I said kappa, but we'll see what happens on the next slide, Hn sigma mod E. Just to reinforce that up to isomorphism, it only depends on the reduction modulo E. So let's see if I've put the right slides on here. So this Hecker algebra only depends on sigma modulo E, but what if we had some more information there? So the combinatorics of this guy and all its Ariki-Cauchy algebras, all its deformations, is controlled by the set of L multipartitions of n. For example, here is a 3 multipartition of 19, because I've got 1, 2, 3 partitions, each, and when I add up all the boxes, I get 19. Okay. Now, given sigma, an arbitrary L-tuple of integers, we can weight these multipartitions. What does that mean? It means that I can, so here I've got an example where sigma is equal to 0, 3, 1. Now notice these numbers are very, very close together, 0, 3, and 1. And notice that these diagrams have been all drawn so that they're all getting in each other's grill. This one is right next to him, and they're all sort of cramped together. Whereas over here, if I pick sigma with larger numbers, they're miles apart from each other, right? But if I reduce them modulo E, which I haven't told you what it is because I can't remember, there is an E for which the reduction of these two things is the same set of numbers. So they label simples and spect modules for the same single Hecker algebra because they reduce mod E to the same thing. But when I draw them, they look different, don't they? And you might be like, why are you drawing them differently? Well, I'll answer that now. What? I think E was 5. E was 5. That sounds like something I would have chosen. Okay, E is 5. So each weighting, like this, gives us a graphically defined ordering on the boxes that I draw. So this is given by their x-coordinates, right? So because I can order boxes, so here, the boxes in different components, you can see that there's a different ordering. So this box here is further to the right than this box here, whereas if I drew it over here, this box is to the left of that box there, right? So if I order these boxes according to their x-coordinates, well, if I change the initial position of these red lines, I'm going to change their initial x-coordinates. So the boxes have different orderings depending on how I draw, what sigma I pick. No, there's no meaning to the height. It's just so that you can see them. But I only care about x-coordinates. Okay. And of course, if I can order the boxes in different ways, well, I can order the multi-partitions in different ways, because I'm just going to say, take the same ordering as we've got on the boxes, and then apply it to the multi-partitions. So I can order the boxes in different ways according to these x-coordinates, which come from keeping track of this extra information sigma, rather than just its reduction mod e. I can then order the multi-partitions similarly, and I can give a different grading according to the x-coordinates too. So all these multi-partitions, as I add the boxes, I could tell you that it has a different grading depending on the x-coordinate. And finally, so this is a theorem of Ariki over the complex numbers. We get a subset, sigma, once you reinterpret the combinatorics, which parameterizes the simple modules of this algebra. And we're going to have to keep track of this sigma so that it doesn't get away from us. And because it's a little sigma for my L-tuple, I might use a big sigma for the subset of multi-partitions which index simple modules. So if I took sigma so that these numbers were really far apart from each other, this guy here would be the set of Kleshev multi-partitions. If I took sigma so that they're really close to each other, this would be what's called the Flottwerb multi-partitions, and that's named after Fodor, Leclerc, Ocado, Thibon, and Welsh. So there are different parameterizing sets for simples of Hecker algebras, and how do you keep track of them? You keep track of them by not forgetting about sigma. You need to remember the actual numbers here, not just their reductions mod e. Question: can we explicitly construct these simple modules? And is the graded decomposition matrix unitriangular with respect to the relevant dominance ordering, right? So I told you that each sigma gives me a different dominance ordering. Are the decomposition matrices unitriangular with respect to that ordering? These are natural enough questions. And a question that subsumes these two questions and gives you a way of proving solving the question is, can we come up with a cellular structure on this one algebra, which only depends on mod e, but like lots of different cellular structures which remember sigma. So I can pick lots of different sigmas, which all give me the same algebra, and I want that each different value of sigma gives me a different cellular structure. Therefore, a different indexing set of simples and a unitriangular change of basis between spect and simple. So if we can answer this question, then the other two are down. Okay, so this was first asked in a sort of different setting by Geck and Rouquier in early 2000s, possibly late 1990s. And I believe they answered it for level 2 for here, so L is 2. Then Geck constructed cellular bases. So he actually answered this very question here over the integers in level 2, and in types B and types D. And he did this for all real reflection groups. Then Geck and Jacon wrote a book, and they did the sort of canonical basic sets for type GL1N. I didn't tell you what a canonical basic set is. It is a way of answering the previous two questions over the complex numbers only, which avoids having to do this. So these canonical basic set ones, they work over C, here, C, C, and they answer the two earlier questions without doing this. So you have two questions which would follow from this. You just answer them rather than constructing this explicitly. But the unfortunate thing is that this only works over the complex numbers. And then Kluveraki and Jacon extended this to all complex reflection groups, but again, only over the complex numbers. And then Kluveraki, Gordon, and Griffith, they didn't construct a cellular basis, but they did show that essentially this is not just a combinatorial thing, this is actually something to do with actual representations of the Hecker algebra. But again, only working over C. And then now, more recently, Bonifay and Rouquier have come up with a conjectural way of doing this, which I know nothing about, so don't ask me, in terms of the Castan-Lustig theory of, I can't even say this, Caligura-Moser spaces. So They are interested in Kasdan-Lustig bases, which are sort of a different flavor. You can't grade them, but they, obviously everyone knows that they have other merits. And they're trying to do this over Z. And this is a theorem. It's got B there, but it's very, 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 very dependent on work of Webster, which was in the setting of this Cherednik algebra that I've told you nothing about, but it was on my title slide, so maybe that counts as okay. This Hecker algebra, which, remember, doesn't depend on sigma, it depends only on the reduction mod E, is free as a Z algebra with a graded cellular basis, and the grading is given by sigma. So here we do care what sigma is, and the ordering on these things depends on sigma. So what am I saying? Yes. Yes, the answer to the question is yes. We can construct these graded cellular bases, so we do know that the decomposition numbers are unitriangular, and okay, sure, we don't actually construct the simples, but you can say, okay, given a cellular basis, we know that you can construct the simples by quotienting out by a radical that I haven't told you about yet. So, sure, we have solved both the questions off the other slide. So, now that we've gone to all this effort to construct these bases, what can I tell you? What was the point? Let's prove some stuff using them. Okay, so here we go. Modular decomposition numbers of Ariki-Koike algebras, and you can forget this last bit because I'm not going to even tell you what that thing is. But this guy is Webster's beautiful thing, which works over fields of positive characteristics. So you may have heard of Cherednik algebras. They're rather the rage. His is better than that because his diagrammatic Cherednik algebras control the representation theory of the Hecker algebra, both over the complex numbers, where they're Morita equivalent to the classical Cherednik algebra, but also over the integers, over a field of arbitrary characteristics, so they're just better. Because the actual Cherednik algebra is a mess over fields of positive characteristics. I think they're just for this Reith product. In the paper that I've been reading, it's just for this Reith product, but he's done a lot of generalization, which might include the other ones, but he doesn't explicitly talk about them as far as I'm aware. So, can we understand the decomposition matrices of Hecker and whatever over arbitrary fields via Kasdan-Lustig theory? Okay, so over C, yes. Rouquier, Chanvarigno-Levasseur proved this, and then later Losev proved it, and later, again, Webster proved it. So over the complex numbers, Hecker algebras and these cellular structures that I just mentioned, they're all controlled by a Kasdan-Lustig theory of sorts. For L is 1 and K is arbitrary, no. So Geordie proved that we can't do this. So you can't use Kasdan-Lustig theory, you need to use something more complicated, P canonical basis. So if you wanted to do it in terms of Kasdan-Lustig theory, because Kasdan-Lustig polynomials are much better understood, they're much easier, people have studied them combinatorially, you might as well put that information to good use. In that case, you would restrict, as we did at the beginning of this talk, to the subcategory labeled by partitions with at most H columns. And a field of P much bigger than H, right? It can't just be bigger than H because then you would have to understand in full the P canonical basis. But you let P be much bigger than H, then we get a simpler, easier to understand picture. So that's what we're going to do. What about higher levels? So what if I take L to be bigger than 1? Well, for an arbitrary weighting, this isn't going to work. You could do a P canonical basis, and in fact, Elias and Losev did do a P canonical basis for the so-called well-separated weighting, which is the classical weighting of Dipper, James, and Mathis. But it can't simplify. You can never get just a regular Kasdan-Lustig theory from it because it includes the symmetric group problem as any sensible subproblem. So what if instead we chose the weighting that I mentioned by Fodor, Leclerc, Ocado, Thibon, and Welsh? Well, if we did that, then we might have a chance. So I'm going to let PLNH denote the set of multi-partitions now with at most H columns in each given component. So here, This guy, there are 40 boxes in this multi-partition, so P40. There are 4 components, 1, 2, 3, 4. There's the 4. And then I have at most 3 columns in any given component, right? So there's a 3 squared there. So the most columns this guy has is 3. So we can let H be 3 here. Well, if we do this, we can quotient out by all the stuff labeled by, so given this Ficada, Leclerc, tralala weighting, we can quotient out by an ideal, a nice ideal. So what is the ideal? Well, I'm going to take these idempotents, EI, and I'm going to consider whenever there's a string of H plus 1 consecutive increasing numbers, I'm going to quotient out by that. So Y, you might think it doesn't look that nice to me. If I have H plus 1 increasing numbers, what does that look like? So these, what's the word? These numbers, what they label is contents of boxes. So if I just stick with the symmetric group for the time being, and I let the first box be of content 1, second one be of content 2, 0, 1, 2, 3, H. What point do I get when do I get H plus 1? Here, so this is exactly when, H plus 1 columns, right? So what does this idempotent say? It says, forget about any idempotent which labels a partition or multi-partition where we have H plus 1 columns. I'm trying to get rid of everything with more than H plus... Oh, yes, sorry, thank you, you're quite right. Increasing from 0, egg on my face. Where would I find a pen now? Thank you. So, there you go. The second you hit too many columns, just say, ugh, don't want that, get rid of it. And that's exactly what this quotient says. So if you were trying to come up in your head a way of getting rid of all things with too many columns, this would be the first sensible thing you would try. And it works. And of course this works, this doesn't really care. You can define this two-sided ideal for any weighting, right? It's a two-sided ideal. It's got nothing to do with the cellular structure. But if you pick your cellular structure nicely enough, this is actually a cell ideal. And the fact that it is a cell ideal means that the quotient algebra that you're interested in also has a cellular structure, so you have a chance at understanding it.
Is there a restriction on what E is compared to H? Or just
there is an inherent restriction based on the fact that I want these numbers, I guess, to be different. E has got to be greater than HL will do it, so I'll just say that. E is greater than HL. And if you think about it, I told you that I was interested in representation theory in terms of these affine actions. So we're going to be looking at the action of an affine Weyl group whose Coxeter number is HL. So this kind of makes sense. So now, given that I've quoted it out by this, and I know enough about the cellular structure, because I picked sigma nicely, I can in fact show that this algebra is quasi-hereditary, i.e. all the simples of this algebra, all the spec modules have simple heads. So this is a generalization of a result of Karen, who in level 1 said, okay, I know that quasi-hereditary things are easier, so I will get rid of all I'll look at the Ringel dual of the general linear group, or if you like, the quotient of the Hecker algebra by, because I've got it here, the idempotent labeled by this guy. So this is well known to be a good idea in level 1. Let's just do it in higher levels. And it's this decomposition matrix appears as a submatrix of that of the full Hecker algebra for just cellular reasons, if you like. And as I just said, this algebra for level 1, so look, 1, is the chunk of Sn we saw earlier in Schur-Weyl duality, or if you like, it's the Ringel dual of the general linear group, or Schur algebra of the general linear group. Now what we want to show is that the representation theory of this algebra, this nice quotient where I've got rid of anything with more than H plus 1 columns, greater than or equal to H plus 1, I want to show that the so I'm obviously going to want the affine Weyl group for LH because I've got L different components, each of which has H columns. So L times H is LH. And this is just, the -1 here is just because the Coxeter number of the symmetric group Sn is Sn minus 1, is minus n minus 1. And now each of these parabolics, of course you have to see a parabolic for each copy of L because it's got to contain the representation theory of the level 1 thing in each of these different chunks, right? I could put all my boxes in one component and that would be the same as looking at the symmetric group. So I've got to see a copy of the dominant region for that relevant thing in each of the L positions. So there are L of these, as you might have guessed, but it's not on the slide. So this would be a great geometry to use. Will it work? So if I let L is 1, so that I cross out all of these other guys, then I get exactly what we talked about earlier, which was AH inside of affine AH. So if L is 1, this is what I see, which is exactly the stuff that I would expect to see in level 1. And if H is 1, what I actually see is just the non-parabolic geometry A hat L minus 1. And this is the geometry that controls Kac-Moody Lie algebras. Lie algebra, GL, L hat. And in this case, this quotient, so we've already seen, okay, this first quotient is the Sn one, which is... Sorry, what? No, there is a hat. Look, there's the hat.
There's no hat on the AH minus 1.
There's not supposed to be. Yeah, this is the geometry that controls level 1. The symmetric group Sn, there is a dominant region, and then there's the action of the affine Weyl group. So that determines the dominant region, and that determines the... So here, remember, I forgot about all of this, and all that said was take orbits. And then I forgot about all of this, and all that is taking orbits. Mm-hmm. Coolio. And here, sorry, is it something on the, anyway, I'm going to carry on. Okay, so, and H is 1, this algebra actually already had a name, and it was called the generalized Blob algebra, which is unfortunate, but it was named by Paul Martin, which is why it's got such a bad name, but it's a very interesting algebra, and it's kind of insane that he conjectured, like, before Cherednik algebras were really getting into the groove or anything like this. He just conjectured, okay, well, there's a quotient like this. He couldn't describe the kernel in a nice way because there was no KLR thing. But he said, okay, there's a nice quotient. I reckon it's controlled by this geometry, AL minus 1. And somehow he was correct, which is insane. Well, I mean... Good on him, I'm not saying. So yes, that's very nice. And again, all that we've done here is embed this via the transpose map in a sensible fashion. And we might see an example, we might not. So we've got the old geometries, which I drew on the board. And these are the ones where L is 1. This is the symmetric group. We've also got the blob geometries that I mentioned. So this is the regular blob algebra. It's controlled by A2 hat. And then this is a generalized blob algebra kind of geometry, or if you like, something to do with Kac-Moody Lie algebras. So same old, fine. But then we see something new. So if we let H and L be greater than 1, we get a geometry that doesn't really appear in classical Lie theory. It does if you're sort of a parabolic category O type of person, but not in like symmetric groups and sort of classical things. So you see a geometry like this, which we might encounter in a bit. So old things, new things. Okay, so we said these geometries should control things. Well, decomposition numbers is a good place to start. So what does this say? This says that the gradient decomposition numbers are given by the associated parabolic affine Castaner-Lustig polynomials. And I've attributed this to myself 3 times and my co-authors. But of course, this is actually implicit in the work of Ruquier, Shan-Varignolu, Vassereau, Lassev, and Webster, but just in a slightly different language. And as a corollary, the decomposition matrix for these generalized blob algebras does have the associated Castanelistic polynomials. And this was the conjecture that Paul Martin and David Woodcock put forward. So here's a new conjecture. Let F be a field of characteristic much bigger than the Coxeter number, which in this case is HL, then the decomposition numbers of this guy should be given by Castanelistic polynomials for lambda mu in this set of multi-partitions that are restricted. And we're looking at the first p-squared alcove, which is something that you would expect to see in any sensible Lustig type conjecture. And we checked it, so it's not just out of the blue. So for certain types of parabolic orbit, so maximal finite parabolic orbits, we can take any field, and this works. I did this for Laurent. If L is 2 and E is infinity, Brunden-Stroppel did this in a different language. Thayers did it for the Hecker algebra as well. Hugh and Mathis did it, and then I guess this is Bowman-Cox at the end. If L is 3 and E is infinity, I don't think anyone did that before us, so it gets its own bullet point. And then again, over the complex numbers, as I said, this is due to a bunch of people before us in a slightly different language, but it's the same result. And finally, if L is 1, then Simon Riesch and Geordie Williamson proved this. It feels it's a backwards logic, but they did prove this. It's not called this. This is somebody else's conjecture then, right? So, but it's proven by Riesch and Williamson that if in the level 1 case, it does work. So that's a good place to start. OK. I guess I can just carry on. I've got time. So, sure, decomposition numbers, great. You can make a conjecture, great. But you have to back up stuff in positive characteristic, because it's not as easy as we once thought it was or hoped it might be. So we're going to say things are generic if they're closer to each other than they are to the walls of the dominant region, which, of course, is meaningless. But let's draw some pictures and see what happens. And the theorem will be, if 2 points are generic, then you can calculate homomorphisms between the associated spect modules. We can construct an explicit homomorphism in this degree. So here's lambda. And so I'm going to consider homomorphisms into spect lambda. So let's consider a single reflection away. And in all these cases, these blue guys are generic. Great. So these are closer to this guy than they are to the walls of the dominant region in some sort of way that can be made precise using paths, but I didn't want to bore you. And then, we can reflect again. So we now got so there's a homomorphism from here to here. There's also a homomorphism from there to there. And the composition of these two things is non-zero and gives me a homomorphism from there to there. And similarly, ding, 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 ding. And all of these ones go down in 2 steps, and you can factorize them. And notice that here I've got here's my little origin. Now if I cut a line up here, you would be seeing something that looked a bit like classical type A for SL3. And there, you would sort of, there would be a homomorphism from there to there, and there would be one from there to there. But in fact there, because these guys are very close to a wall, you would actually find that there was no homomorphism from there to there. But there is now, because we're using a different geometry. So locally, you can see these sort of like things that look like Carter-Payne homomorphisms, things that we're used to. But over here, ding, whoa, I'm reflecting all the way over here. This kind of thing doesn't happen in the symmetric group world. You don't get these massive gaps where you can reflect long distances. But these new things crop up here. And then you can reflect again. We're still generic. All of these things give us homomorphisms. And here, this guy here, he doesn't give us a homomorphism. Because notice that, like in the SL3 case, I sort of go, oop, oop. And this is too close to a wall going through these 2 reflections. So stuff doesn't pan out. But in all the colored ones, which aren't black, these all give homomorphisms into this guy. And you can do them via chains, which essentially amount to nothing more than the strong linkage principle. There's a homomorphism if and only if they're strongly linked. And in fact, if you let H be 1, so we're looking at Paul's generalized blob algebra here, every single pair of weights that are strongly linked have a homomorphism relating them. And here, I've put this Q notation here, but everything lifts to the full Hecker algebra. So You have to pick the nice weighting, of course, in order to to construct these spect modules, but everything lifts, so homomorphisms between spect modules labeled by one-column multi-partitions are that you can always construct them, and you can always look at their compositions, and they're always lovely. So finally, an example, and I thought I'd just sort of, in case you don't like KLR algebra stuff, I thought I'd rephrase this in terms of Hecker algebra stuff. So let's let n is 13, so we're looking at S13, wreath, the cyclic group C2. And I've used the good old-fashioned notation of Q1 and Q2. So this is a deformation of the hyperoctahedral group, if you like. I went really old school with this slide. So I'm going to let E is 5, so this must be the same E is 5 as Andrew spotted earlier. And I'm going to pick these values for my deformation parameters. I'm going to pick an arbitrary ring, because arbitrary field, because everything works over an arbitrary field. Whoa, so I'm going to embed all the bipartitions. So bipartitions are the things that label modules for the Hecker algebra of type level 2. So they're all of the form, if I'm going to restrict to bipartitions, it's all lambda comma mu. Now I'm also restricting so that it fits into, I want it to fit into two-dimensional space, so I've also restricted by restricting this guy a bit further. So I've got 1, 2, 3 different numbers here, right? So just like before, I go, I'm bouncing. Plus epsilon 1. So because it's, we can project down from three-dimensional space to two-dimensional space, I can label something by 3 numbers, A, B, and C, and put it into this plane. And these label all of the guys in a particular block that I'm interested in for this Hecker algebra. So these all label representations, and these are all the representations of this particular form here. Now what am I going to say? So these different regions, so this looks like a Steinberg vertex for the normal, good old-fashioned symmetric group, or SL3, whatever you want to call it. And here, locally, this behaves like a Steinberg vertex. So I get compositions of homomorphisms going around it all nicely like that. Here, this is another thing that looks like a Steinberg vertex, so I get nice homomorphisms around here like that. And here, this looks like the edge of the dominant alcove for SL3. So not Steinberg, but something else that we're familiar with. So then when I compute the decomposition table on the other slide, I get something that looks like, so here's M. So if the colors match, then it's something that I can do using entirely classical SL3 theory. So M here, so if I go back to here, this looks like a Steinberg vertex, so the decomposition numbers around this vertex are the Castaner-Lustig polynomials, aspifying Castaner-Lustig polynomials with no parabolic. Similarly here. Or if you like, just tilting multiplicities for SL3. Tilting multiplicities for SL3. Something different. So tilting multiplicities for SL3, tilting multiplicities for SL3, and then, because I can actually reflect this whole hexagon to that whole hexagon, I actually encounter t to the 1 times tilting multiplicities for SL3, and then a whole bunch of other stuff which I can also calculate using these generic homomorphisms. And this all works over fields of arbitrary characteristic because, well, the Castaner-Lustig conjecture, if you like, works in type A2, and that should have a hat on. So for the same reason, we can calculate these things in arbitrary characteristic. So I guess I'm done. Yeah, so I won't talk about that. Okay, thanks very much. I don't know. Geordie, do you know? Can decomposition number, can p-canonical bases things, can the multiplicities grow unboundedly?
We conjecture that I'll discuss on Tuesday is that they grow exponentially.
There you go. So we get big. Okay.
Your form for the decomposition numbers, do you have some sufficient conditions for it for the form to always be achieved or something?
No, I don't. I guess it would be rarely, I suppose. it's sort of another way of writing down sort of classical Castanelistic theory. What's nice about it is that these paths, so they basically encode Castanelistic theory, but in a path theoretic way, which I guess is, the idea comes from Wenzel and Fred's paper. This is just a sort of reimagining of it. What's really cute is that if you take the diagrammatic chain-reading algebra, these things aren't just like, oh, I've got some paths, oh, great. They actually index a basis of that algebra, and that algebra is a quasi-hereditary cover of the symmetric, well, of the relevant complex reflection group. So we get decomposition number bounds really easily because we just say, well, you can't have more decomposition numbers than there are highest weights there, so that's sort of how that works. But it's sort of Castanelistic theory in just another guise, so
So just now when you say that the bounds are sharp, so that the bounds are all not achieved in those states.
yeah. So if you, for example, if you do a single reflection, the bound will always be achieved, and that'll be fine. But as you do more and more complicated reflections, things will get they'll get further away from being sharp.
Are these Q algebras Kazoo?
Over C, they're Kazoo, because they're Morita equivalent to the classical Schrödinger algebras.